Tonight, we're going to follow a telescope into the past and watch what it found there. Not a metaphorical past, a literal one. The James Webb Space Telescope, launched on Christmas Day 2021, is designed to look so deep into space that the light it collects left its sources before the Earth existed, before the Sun existed, before any galaxy in the observable universe had finished building itself. The light arriving at Webb's golden mirrors right now has been travelling for more than 13 billion years. When that light left, the universe was a few 100 million years old. The temperature had fallen enough for the first atoms to form, for gravity to begin pulling hydrogen and helium together into the first stars, for those stars to begin burning and dying and seeding the surrounding gas with the first heavy elements. It was the beginning of everything that would eventually become us. Tonight, what Webb found there was supposed to confirm our best model of how the universe grew up. Instead, it found something that has sent cosmologists back to their equations. The galaxies Webb saw in the early universe were not the fragile, diffuse, slowly assembling structures that our best models predicted. They were massive, structured, chemically complex, in some cases indistinguishable in appearance and composition from galaxies that, according to the standard model, should not have existed for billions of years after the moments we were observing. The standard model said the early universe was a construction site, full of raw materials slowly being assembled by gravity into the first small galaxies, which would themselves slowly merge into larger ones over cosmic time. Webb looked at the construction site and found that some of the buildings were already finished. Tonight, we're going to spend the entire night understanding what that means. We're going to begin with how the standard model was built, what observations it explains, why it was trusted so completely before Webb launched, and exactly what it predicted the early universe should look like. We're going to examine the specific observations that are challenging it, galaxy by galaxy, redshift by redshift, stellar mass by stellar mass. We're going to explore the leading explanations for the discrepancy, early dark energy, modified gravity, primordial black holes as seeds for rapid galaxy formation, and the possibility that our models of how quickly stars can form in extreme conditions are simply wrong. We're going to examine the Hubble tension, the growing disagreement between two methods of measuring the universe's expansion rate, which connects to the galaxy problem in ways that make both anomalies harder to dismiss. And we are going to consider what it would mean for cosmology if the standard model needs substantial revision, not replacement but revision, in its account of the universe's first billion years. By the end of tonight, you will have a thorough picture of what Webb is showing us, why it is surprising, and why the scientific community is taking it seriously without yet claiming that everything we thought we knew is wrong. By the end of tonight, we want you to carry something with us. The fact that a single telescope, launched a few years ago and pointed at the oldest parts of the sky, has given cosmology a set of homework problems that will take a generation to work through. That is not a crisis. That is science functioning exactly as it should. The model is being tested and the model is being revised. The universe is telling us something. We're just beginning to understand what. We make long-form sleep documentaries about space and cosmology. If tonight is your first time with us, the link in the description will bring you back. New episodes arrive every week. Now let's begin. On Christmas Day 2021, a rocket carrying the James Webb Space Telescope lifted off from the Guiana Space Center in South America and began what would become the most complex and consequential deployment in the history of space astronomy. Webb spent the next 30 days travelling to its operational position, the second Lagrange point, roughly 1 million miles from Earth in the direction away from the Sun. At L2, the gravitational pulls of the Earth and Sun, combined with Webb's orbital velocity, allow it to maintain a stable position relative to Earth while both orbit the Sun. Being far from Earth means the telescope is shielded from the majority of the Earth's heat and light radiation. Being in a stable orbital position means its instruments can operate at extremely cold temperatures without constant station, keeping maneuvers. The deployment sequence was nicknamed by engineers 30 Days of Terror, and by everyone else who understood what was at stake as something considerably more anxiety-inducing. The telescope's primary mirror, 21 feet in diameter, was too large to fit inside any existing rocket fairing in its final configuration, and had to be folded origami, style for launch, and then unfolded precisely in space. The sun shield, a 5-layer membrane the size of a tennis court designed to block the heat and light of the sun, Earth and Moon from the telescope's instruments, also had to unfold in a sequence involving 344 single-point failures, any one of which would have ended the mission. If any one of the 344 mechanisms failed, the mission would be compromised or destroyed. Everything worked. By January 24, 2022, Webb had completed its deployment and was in its operational orbit. The mirror segments were then aligned over a period of months with a precision measured in nanometers, and the instruments were brought to operational temperature approximately 40 degrees above absolute zero for the primary mirror and 7 degrees above absolute zero for the MIRI mid-infrared instrument, which requires cooling to temperatures colder than the background of the deep space. First science images were released publicly on July 12, 2022. The images showed a gravitational lensing cluster, a stellar nursery, the Southern Ring Nebula, Stephan's Quintet, and what was called the Deep Field. A tiny patch of sky, smaller than a grain of sand held at arm's length, containing thousands of galaxies at vastly different distances. Many of those galaxies had never been imaged before. Some of them appeared to be from the very early universe. The trouble, from a cosmological standpoint, began immediately. By the end of tonight, the trouble was not with Webb. It was with what Webb found. Tonight, to understand why what Webb found was so surprising, we need to understand the epoch it was looking into. And we need to understand it concretely, not as a general description of the early universe, but as a specific sequence of events with specific durations and specific physical conditions. The Big Bang occurred approximately 13.8 billion years ago. In its immediate aftermath, the universe was an extraordinarily dense, extraordinarily hot plasma, a sea of fundamental particles, photons, and energy in a state of thermal equilibrium. It was opaque. Photons scattered continuously off free electrons and could not travel any significant distance. The universe was, in the most literal sense, completely dark to any form of electromagnetic observation. For the first 380,000 years after the Big Bang, this opacity continued. Then the universe cooled enough, to roughly 3,000 degrees Fahrenheit, for electrons to combine with protons and form neutral hydrogen atoms. This event is called recombination, and it marks the moment when the universe became transparent to light for the first time. The photons that had been trapped in the plasma streamed freely in all directions, and that radiation, cooled by 13.8 billion years of cosmic expansion to just a few degrees above absolute zero, is the cosmic microwave background we detect today. After recombination, the universe entered what cosmologists call the cosmic dark ages. The neutral hydrogen filled the space between whatever small proto-structures were beginning to form. There were no stars yet, no galaxies, no sources of light of any kind except the fading afterglow of the Big Bang itself. The universe was dark, cold, and filled with a neutral hydrogen fog that would have been impenetrable to the kinds of visible and ultraviolet light we use to observe galaxies. The Dark Ages lasted from approximately 380,000 years after the Big Bang to somewhere between 100 million and 300 million years after the Big Bang. During this period, the first dark matter halos were slowly assembling, gravity pulling together the slightly over-dense regions left by the quantum fluctuations of inflation. Gas was falling into those halos, molecular hydrogen was forming in pockets where conditions allowed, and molecular hydrogen is a critical coolant. It can release energy in ways that allow gas to collapse further and reach the densities needed to initiate nuclear fusion. The first stars, sometimes called population 3 stars, ignited somewhere in this range. These stars were extraordinarily massive. In the absence of heavy elements, which are efficient coolants in the late universe star formation process, the primordial gas could cool only through molecular hydrogen. Less cooling means gas collapsed into larger and hotter clumps before fusion ignited, producing more massive stars. Theoretical models suggest population 3 stars had masses ranging from a few tens of solar masses to potentially hundreds of solar masses, burning at extraordinary temperatures for mere millions of years before exploding in supernova so energetic they dispersed their material across enormous regions of the surrounding intergalactic medium. The death of the first population 3 stars did two things simultaneously. It enriched the surrounding intergalactic medium with the first heavy elements, primarily carbon, oxygen and silicon, seeding the raw material for the next generation of smaller, longer-lived stars. And it began the process of reionization. The intense ultraviolet radiation from these massive stars and from their deaths began to ionize the neutral hydrogen in the surrounding universe. No one expects the transition from the Dark Ages to the first light to be a smooth, uniform event. The current understanding is that it was patchy and extended. Isolated pockets of ionized hydrogen surrounded individual stars, forming regions and young proto-galaxies. These ionized bubbles expanded as more stars formed, eventually merging and overlapping until the entire intergalactic medium was reionized, sometime around 900 million years after the Big Bang. Webb cannot directly observe the Dark Ages. Neutral hydrogen absorbs light so completely in certain wavelength ranges that no electromagnetic signal from before the first stars can reach us. What Webb can observe is the tail end of the Dark Ages and the first bright objects that lit up after them, the first galaxies and quasars at redshifts above 10, which are precisely the objects causing the timeline problem. The 21 centimetre radio emission of neutral hydrogen is the one observational window into the Dark Ages. Neutral hydrogen emits at this wavelength when the electron spin in the atom flips from aligned with the proton spin to anti-aligned. By observing this emission at different radio frequencies, each corresponding to a different redshift, radio telescopes can in principle map the three-dimensional distribution of neutral hydrogen through the Dark Ages, tracking when and where reionization occurred. This is an extraordinarily difficult observation because the 21 centimetre signal from the cosmic dawn is many orders of magnitude fainter than terrestrial radio interference. The Square Kilometre Array, currently under construction in Australia and South Africa, is designed with this observation as one of its primary science targets. The connection to Webb's early galaxy problem is direct. Every constraint Webb places on the properties of early galaxies constrains the timing and character of reionization, which constrains what the Dark Ages were like, which constrains the nature of the first stars and the rate of early structure formation. The Webb observations, the theoretical models of the Dark Ages, and the future 21 centimetre observations are all windows onto the same sequence of events, approached from different observational angles. The Dark Ages are not merely a poetic name for an inaccessible epoch. They are the specific period during which the seeds of everything Webb is now observing were laid. The first dark matter, halos, the first population 3 stars, the first chemical enrichment of the intergalactic medium, the first bubbles of ionized hydrogen. All of that happened in a period of a few 100 million years that we cannot observe directly, and whose properties we are inferring from the galaxies that emerged from it. Webb is showing us those galaxies in unprecedented detail, and they are not quite what we expected to find. To understand what Webb found that was surprising, we need to understand what the standard model of cosmology predicted it should find. This model, called Lambda Cold Dark Matter, or CDM, is the framework within which all of modern cosmology has operated for the last 3 decades. It is, by any reasonable measure, one of the most successful scientific theories ever developed. CDM gets its name from its two most important and least understood components. Lambda, the cosmological constant that represents dark energy, the unknown quantity accelerating the universe's expansion, and cold dark matter, the unknown form of matter that does not interact with light, but does interact gravitationally and constitutes roughly 85% of all the matter in the universe. The model describes the evolution of the universe from its earliest moments to the present day, and it is successful in a profound and specific sense. It makes quantitative predictions about the large-scale structure of the cosmos, the distribution of galaxies across the observable universe, the temperature fluctuations of the cosmic microwave background, the relative abundances of hydrogen, helium and lithium produced in the first few minutes, and the rate of cosmic expansion, and those predictions match observations with extraordinary precision. The cosmic microwave background is the thermal afterglow of the early universe, light emitted 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons into neutral hydrogen, allowing light to travel freely for the first time. The Planck satellite, operated by the European Space Agency, mapped this background radiation with sufficient precision to measure the universe's composition. Ordinary matter constitutes roughly 5% of the total energy budget, dark matter roughly 27%, dark energy roughly 68%. CDM predicted these fractions and the observations confirmed them. The CDM model also makes specific predictions about galaxy formation, and this is where the Webb observations become interesting. The model describes galaxy formation as a hierarchical process, meaning galaxies build from the bottom up. Small structures form first. Large structures form later by accumulation and merger. Here is why the hierarchy works this way. In the early universe, the dominant material was dark matter. Dark matter interacts gravitationally, but not with light or ordinary matter, in ways that would heat it up or push it around. After the Big Bang, dark matter was distributed almost uniformly through space, with tiny quantum fluctuations, density variations of roughly 1 part in 100,000, seeded by inflation in the universe's first fraction of a second. Gravity amplified these tiny fluctuations. Regions slightly denser than average attracted surrounding matter. Less dense regions gave matter up to their denser neighbours. Over time, the dark matter collapsed into vast filamentary networks, halos within filaments, and the cosmic web of large-scale structure we observe in galaxy surveys today. The first dark matter halos to form, in CDM, are small. The smallest halos collapse first because they are the first overdensities to reach the threshold for gravitational collapse. Gas falls into these small halos, cools, and begins forming the first stars. The first stars were enormous by the standards of stars today, potentially hundreds of times the mass of the Sun, burning bright and hot and fast and dying in spectacular supernovae within a few million years. These stellar deaths enrich the surrounding gas with the first heavy elements. Over the next few 100 million years, small dark matter halos merged into larger ones. Small galaxies merged into larger galaxies. The hierarchical assembly continued up the mass scale, producing progressively larger structures over progressively longer timescales. A galaxy the mass of the Milky Way, roughly 100 billion solar masses in stars, was expected to require several billion years to assemble through this hierarchical merging process. By the end of tonight, CDM predicted that the very early universe, the universe as it existed in its first few 100 million years, should contain only small, irregular, low metallicity proto, galaxies in the early stages of assembly, not completed galaxies, not massive, organized stellar systems, rough fragmentary primitive structures still in the process of building themselves up. The simulations were detailed and specific. The Illustrious simulation, later upgraded to Illustrious TNG, modelled the gravitational evolution of billions of particles of dark matter and ordinary matter through cosmic time, incorporating star formation, supernova feedback, black hole accretion, and the radiative effects of young massive stars. These simulations made concrete predictions about what Webb should see when it looked back to the universe's first 500 million years. The predictions were clear: at redshifts above 10, meaning at cosmic look-back times greater than about 13.3 billion years, the simulation predicted the galaxy population should consist primarily of small, faint diffuse structures. Individual galaxies at these distances should be low in stellar mass, meaning they should not yet have converted much of their gas into stars. They should be low in heavy element abundance, reflecting their early stage in the stellar evolution cycle, and they should be structurally simple, without the organized disk or elliptical morphologies that require many billions of years of dynamical relaxation to develop. This was the consensus expectation before Webb launched. It was supported not only by theoretical models but by the observational capabilities of Hubble, which had reached to redshifts around 11 in its deepest images and found, consistent with CDM predictions, a population of faint, small, irregular galaxies that looked like construction sites. What Webb found, with its vastly superior infrared sensitivity, was different. No one expects a telescope built to confirm a model to instead challenge some of that model's fundamental predictions. But that is what happened in the first 18 months of Webb's operations, and the challenge came not from a single anomalous galaxy, but from a statistically significant population of objects that should not have been able to form in the time available. The galaxies that caused the immediate alarm were not found one by one as Webb's science program was carefully executed. They appeared almost immediately in the preliminary data, before Webb had even completed its commissioning phase. In the summer of 2022, while the telescope was still in its calibration period, astronomer Rohan Naidu and his colleagues at MIT identified 6 candidate galaxies in the early Webb imaging data that appeared to be at extraordinarily high redshifts, the most distant of them possibly at redshift z equal to 17. Redshift is the key quantity here. When the universe expands, the wavelength of light travelling through it stretches. A galaxy at redshift 0 is at our position. A galaxy at redshift 1, the universe is twice as large now as it was when that light left. A galaxy at redshift 10, the universe is 11 times larger. A galaxy at redshift 17 would have emitted its light when the universe was roughly 250 million years old, a cosmic eye blink after the Big Bang. The 6 Naidu candidates, if confirmed, would have contained stellar masses of between 100 million and 5 billion solar masses. For context, 250 million years is not a long time for galaxies to accumulate that much stellar mass under the conditions CDM predicts. The model was not comfortable with those numbers. Subsequent spectroscopic confirmation reduced the Naidu sample. Several of the candidates turned out to be at lower redshifts than the photometric estimates suggested, a known risk of photometric redshift estimation that astronomer after astronomer cautioned about. Photometric redshifts, estimated from the colours of a galaxy in different wavelength bands rather than from the detailed measurement of spectral lines, can be uncertain, especially for objects observed in only a few wavelength bands. Webb's NIRCam instrument, which captured the initial images, is a camera, not a spectrograph. Photometric redshifts are preliminary estimates that require follow-up spectroscopic confirmation to be trusted at the precision required for statements about galaxy masses at high redshift. When spectroscopic follow-up arrived, the picture became both clearer and more complicated. Maisie's galaxy, named after astronomer Stephen Finkelstein's daughter, whose birthday coincided with its discovery, was confirmed spectroscopically by the JD survey in 2023 at a redshift of approximately 11.4, placing it at a look-back time of roughly 13.4 billion years, just 390 million years after the Big Bang. Its stellar mass was estimated at a few hundred million solar masses. The JD survey, the JWST Advanced Deep Extragalactic Survey, was the most systematic early universe-galaxy census in Webb's first 2 years of operation. The survey used hundreds of hours of telescope time across deep imaging and spectroscopic modes to characterize thousands of galaxies at high redshift. In early 2024, the JADES team announced the spectroscopic confirmation of JADES GS Z14-0, a galaxy at redshift 1432. This is the most distant spectroscopically confirmed galaxy as of mid-2026. JADA's GS Z14-0 is astonishing for several reasons. It is not at a preliminary photometric redshift estimate. It is spectroscopically confirmed, meaning its redshift is measured from the precise wavelengths of known atomic emission lines, the same technique used by astronomers for a century on nearby galaxies but now applied to light that left its source when the universe was 290 million years old. At redshift 1432, JADA's GS Z14-0 has a stellar mass of roughly 500 million solar masses and is producing stars at an impressive rate, a few solar masses per year. It is also large, physically extended to about 1,600 light years across, meaning it occupies real physical space rather than being a compact single burst of star formation, and its light spectrum shows clear evidence of oxygen emission, meaning the galaxy had already gone through at least one generation of massive stars that synthesized oxygen through nuclear fusion and then expelled it into the surrounding gas through stellar winds and supernovae. Oxygen in a galaxy at 290 million years old is a quiet, systematic problem for standard formation models. The standard model says the first stars were metal, free, composed of only hydrogen and helium, because those were the only elements produced in the Big Bang and in the first few million years of stellar evolution. For a galaxy to show detectable oxygen emission at redshift 14, it had to have formed its first generation of massive stars. Those stars had to have lived their brief lives and exploded as supernovae. Those explosions had to have enriched the surrounding gas with oxygen, and that oxygen, enriched gas, had to have formed a second generation of stars. All of this had to have happened within the first 290 million years of the universe's existence. That is possible. It is not, strictly speaking, impossible within the framework of CDM, but it is at or beyond the edge of what the standard model considered plausible. Galaxy GN Z11 has a somewhat longer scientific history. First identified in Hubble imaging, it was confirmed at a redshift of approximately 10.96 by ground-based spectroscopy in 2016, making it then the most distant confirmed galaxy. Webb has since observed GN Z11 extensively, and what it found there elevated the galaxy's scientific interest considerably. In 2023, a team led by Roberto Maiolino reported the detection in GN Z11's spectrum of unexpected emission lines that suggested the presence of a highly luminous active galactic nucleus, a supermassive black hole in the process of actively accreting material. A supermassive black hole in a galaxy at redshift 10.96 required that not only had the galaxy formed early, but that a black hole of millions of solar masses had also assembled at its centre in a time the standard model finds difficult to accommodate. The GN Z11 black hole finding connects to a broader and separate observational tension: the discovery of quasars at high redshift in surveys predating Webb. Quasars are extraordinarily luminous active galactic nuclei powered by supermassive black holes accreting material at high rates. Surveys with ground-based telescopes and with Hubble had, before Webb launched, identified quasars at redshifts above 6 and 7, meaning supermassive black holes of more than 1 billion solar masses had assembled within the first billion years of the universe's history. Black holes of that mass, under standard models of black hole growth, require enormous amounts of time to assemble through accretion, even starting from massive seed black holes, and the time available in the early universe was uncomfortably short. Webb has extended the quasar sample to even higher redshifts, and has also found a population of compact reddish objects that do not quite match the profile of typical high, redshift galaxies or typical quasars, called little red dots by some researchers. These objects, dozens of which have been identified, appear to be compact and extremely luminous, consistent with active black holes in very early galaxies that are being observed at a phase in their growth not well captured by pre-Webb models. By the end of tonight, the catalogue of anomalous early universe objects from Webb is not a handful of outliers. It is a statistically significant sample that collectively pushes on the standard model from multiple directions simultaneously. The masses are too high, the formation timescales are too short, the chemical enrichment is too advanced, and the black holes are too large. Each individual object could be explained away with carefully calibrated model adjustments. The ensemble requires something more systematic. No one predicts that a telescope designed to fill in the details of a well-established model would instead find that the details need to be reconsidered. And yet that is what Webb did, beginning almost from its first days of observation. Understanding why Webb is capable of seeing what Hubble could not requires, understanding why infrared light is the right tool for this particular task, and why building an infrared telescope in space involves engineering challenges of a different order of difficulty from those faced by every previous observatory. The key is redshift. When a galaxy at redshift 14 emits ultraviolet light, that light arrives at Earth with its wavelength stretched by a factor of 1 plus z, in this case 15. Ultraviolet light at 100 to 200 nanometers, emitted by hot young stars, arrives at Earth at wavelengths of 500 to 3000 nanometers, squarely in the near infrared. The visible light that young stars emitted in JADE's GS Z14-0 arrives at Earth in the mid-infrared. Hubble, primarily designed for ultraviolet and visible observation, can observe in the near-infrared to some extent, but its longest wavelength instrument, WFC3, reaches only to about 1/700 nanometers, and its sensitivity falls steeply beyond about 1000 nanometers. Webb's primary science instruments cover wavelengths from 0.6 to 28 microns, approximately 1 to 45 times the wavelengths visible to the human eye. The two workhorse instruments for high redshift galaxy science are NIRCam, the near-infrared camera covering 0.6 to 5 microns, and NIRSPEC, the near-infrared spectrograph covering 0.6 to 5.3 microns. MIRI, the mid-infrared instrument, extends coverage to 28 microns and is particularly useful for detecting thermal emission from cool dust in the most distant galaxies. The size of Webb's primary mirror is 21.3 feet in diameter, compared to Hubble's 7.9 feet. In angular resolution, a telescope's ability to distinguish fine detail, resolution scales with the mirror diameter divided by the observing wavelength. At the same wavelength, a larger mirror resolves finer structure. The fact that Webb observes at wavelengths roughly 10 times longer than Hubble's primary science bands would, naively, reduce its angular resolution. In practice, the larger mirror compensates, and Webb achieves angular resolutions comparable to Hubble at infrared wavelengths that Hubble cannot observe at all. The mirror is composed of 18 hexagonal beryllium segments, each coated with a microscopically thin layer of gold. Gold is chosen for its high reflectivity in the infrared. The segments were aligned with nanometer precision after deployment, a process that took approximately 4 months. Misalignment of any segment by more than a tiny fraction of the observing wavelength would produce a blurred image. The engineering challenge that makes infrared astronomy in space so demanding is thermal noise. Every warm object emits infrared radiation in proportion to its temperature. A telescope at room temperature would be blazing in the infrared, completely swamping the faint signals from distant galaxies. Hubble operates at temperatures only slightly below room temperature, which limits its infrared sensitivity. Webb's primary mirror and science instruments must be maintained at approximately minus 388 degrees Fahrenheit, about 40 degrees above absolute zero, to reduce the thermal noise from the telescope itself to a level where the faint infrared signals from early galaxies can be detected. The sun shield achieves this by blocking the radiation from the Sun, Earth, and Moon. The 5-layer shield, each layer a thin sheet of a material called Captain coated with aluminum on both faces, and silicon on the Sun, facing face of the outermost layer, reduces the heat load on the cold side of the telescope by a factor of roughly 1 million. The hot side of the shield faces the sun and reaches temperatures around 230 degrees Fahrenheit. The cold side, in permanent shadow, reaches temperatures cold enough to cool most of the telescope's optical system to the required operating temperature. The MIRI instrument requires active cooling below 7 degrees above absolute zero, which it achieves with a mechanical cryocooler. The cryocooler is the only moving part in Webb's science instruments, and it operates continuously throughout the mission. Tonight, when the numbers from JADE's GS Z14 Neo appear in a scientific paper, they are the product of photons that left a galaxy 290 million years after the Big Bang, travelled 13.5 billion light years through an expanding universe, passed through Earth's atmosphere and into space, and struck a gold-coated beryllium mirror operating at 40 degrees above absolute zero. The signal in the detector that recorded those photons represents quantum transitions in atoms in a galaxy that existed before our solar system, before any of the stars visible to the naked eye, before the heavy elements necessary for rocky planets had been substantially distributed through the interstellar medium of the Milky Way. The detector that recorded those photons, the NIRSPEC Micro Shutter Assembly, is a grid of 250,000 individually controllable shutters, each 82 microns wide and 173 microns tall. The shutters open or close electronically in patterns programmed by astronomers on Earth, allowing selected target objects to admit their light to the spectrograph, while blocking light from everything else in the field of view. Selecting 100 targets simultaneously with this system requires precise knowledge of where each target is on the sky, derived from prior imaging and coordination between the telescope's pointing, the shutter programming, and the spectrograph's calibration. No one expects the engineering behind a single redshift measurement to span gold, coating technology, cryogenic refrigeration, micro-scale electronic shutter arrays, quantum mechanics, and the physics of the expanding universe simultaneously. But that is the reality of what produces the calibration counts that are surprising the cosmological community. The investment is returning discoveries at a rate that surpassed even the optimistic predictions of the mission planners. By its third year of science operations, Webb had spectroscopically confirmed more galaxies at redshifts above 8 than had been confirmed in the entire pre-Webb era. The sample statistics are now large enough to draw reliable conclusions about the galaxy population at these epochs, and those conclusions are what is creating the tension with the Standard Model. Independently of the early galaxy problem, Webb has also been contributing to the resolution, or rather the deepening, of a separate cosmological tension that predates its launch, and that connects to the galaxy timeline problem in ways that are not obvious but matter enormously. The tension is about the expansion rate of the universe. The universe is expanding. Edwin Hubble established this observationally in 1929, when he measured the distances and recession velocities of nearby galaxies, and found that more distant galaxies were receding faster in proportion to their distance. The proportionality constant, called the Hubble constant and denoted h0, describes how fast the universe is currently expanding. Expressed in the standard notation astronomers use, it describes how fast 2 points separated by a megaparsec, roughly 3.226 million light years, are moving apart from each other due to cosmic expansion alone. The value of h0 matters enormously. It sets the age of the universe, because if you run the expansion backward, h0 combined with the rate of change of expansion tells you when the universe was packed into a single point. It sets the distances to all objects in the universe measured by redshift, and it is a fundamental parameter of the CDM model whose value should be predictable from early universe physics and consistent with direct measurements. It is not consistent. That inconsistency is now one of the most significant unresolved problems in cosmology. The early universe measurement comes from the cosmic microwave background. The Planck satellite measured the temperature fluctuations of the CMB with extraordinary precision and used those measurements to determine the cosmological parameters, including H0, within the framework of CDM. The Planck measurement gives a value of H0 near 67.4 in the standard cosmological unit, with an uncertainty of less than 1%. The late universe measurement comes from the cosmic distance ladder. Astronomers measure distances by calibrating nearby distance indicators against each other. In the first rung of the ladder, precise distances to nearby stars are measured using parallax, the tiny shift in apparent position of a star as Earth orbits the Sun. In the second rung, those parallax distances are used to calibrate Cepheid variable stars, which pulsate with a period that is precisely related to their intrinsic luminosity. In the third rung, Cepheids in nearby galaxies calibrate type Ia supernovae, stellar explosions that have a well-characterized peak luminosity. Type Ia supernovae can be seen across billions of light years, and their apparent brightness then tells us their distance, which combined with their recession velocity gives H0. The HHS collaboration, led by the Nobel Prize winner Adam Rees at Johns Hopkins University, used the distance ladder method and found H0 approximately equal to 73.0 in the same units. The discrepancy between 67.4 and 73.0 is now more than 5 standard deviations, the threshold physicists use to call something a discovery. A 5 sigma discrepancy would be a significant finding, even if it arose by chance only about one time in 3.5 million experiments. The tension has persisted through a decade of increasingly careful measurements on both sides. Rees and the SHIES team have improved their calibration at every step of the distance ladder, using Gaia parallax measurements of extraordinary precision, using Hubble observations of Cepheids in nearby galaxies, and ultimately using dozens of Type Ia supernovae to measure H0. Each improvement has tightened the uncertainty without reducing the tension. The expectation when Webb launched was that it would help resolve the tension by independently calibrating the distance ladder at levels of precision beyond Hubble's capability. Webb can observe Cepheids at greater distances and with better sensitivity than Hubble, potentially revealing whether any systematic errors had crept into the Hubble-based calibrations. Webb's results on the Hubble tension have been broadly confirming of the tension rather than resolving it. A 2023 study by Rees and colleagues using Webb's NIRCam instrument to observe Cepheids in NGC 43258, the galaxy used as the anchor for distance ladder calibrations, confirmed the Cepheid distances measured by Hubble, and found no evidence for the kind of crowding or blending of stellar images that some had suggested might be introducing systematic errors. The SHIES value of H0 near 73 held up under Webb's scrutiny. A different approach to the late universe measurement comes from the Carnegie Chicago Hubble program, led by the astronomer Wendy Friedman at the University of Chicago. Friedman's team uses a different set of distance indicators, the tip of the red giant branch stars and carbon stars rather than Cepheids, and obtains values of H0 that have historically fallen between the Planck value and the SHIES value. In 2024, Friedman published an analysis using Webb observations of tip of the red giant branch distances in several nearby galaxies and arrived at a value of H0 close to 70 or 71, in moderate tension with both the Planck value and the SH0ES value. The situation is genuinely unsettled. 3 methods of late universe measurement are giving 3 somewhat different answers, all of which disagree with the early universe Planck value to varying degrees. The minimum conclusion is that the Planck value and the SH0ES value are inconsistent at a level that cannot be explained by measurement uncertainties alone. The maximum conclusion, that CDM is missing something fundamental in its account of the universe's expansion history, remains possible. By the end of tonight, the Hubble tension connects to the early galaxy problem in the following way. If the expansion rate of the universe is actually higher than the Planck value, as the distance ladder measurements suggest, then the age of the universe is somewhat younger than the CDM prediction of 13.8 billion years. A universe that is younger has less time available for galaxies to form. A shorter available time makes the early massive galaxies Webb is finding even harder to explain. The two anomalies point in the same direction. The standard model may be missing something that affects how fast structure forms in the early universe. No one predicts that two of the most successful cosmological measurements ever made, the Planck CMB measurement and the Schwarz distance ladder, would arrive at inconsistent values for the universe's most fundamental parameter. They have, and they continue to. The cosmological community has proposed several explanations for the early galaxy problem and the Hubble tension, and it is worth working through them carefully, because the explanations range from modest adjustments to the existing framework to substantial revisions of fundamental physics. The first and most conservative explanation for the unexpected early galaxy masses is that the stellar mass estimates are wrong. Estimating the mass of a distant galaxy from its light is a complex inference that depends on assumptions about the age distribution of stars, the initial mass function describing how many stars of each mass form per star formation event, and the dust content of the galaxy. Dust absorbs light, making a galaxy appear fainter and therefore potentially less massive than it really is, or in some configurations causing estimators to misidentify the stellar population. If the stellar mass estimates for high, redshift Webb galaxies are systematically overestimated by a factor of 2 or 3, the tension with the standard model is substantially reduced. Several studies have explored this possibility. The results are mixed. Summary analyses of the same galaxies using different spectral energy distribution fitting methods do produce lower stellar mass estimates. Others confirm or increase them. The emerging consensus, not yet fully settled, is that stellar mass overestimation can account for some but not all of the excess. The most extreme early galaxy outliers remain problematic, even under conservative stellar mass assumptions. The second explanation involves the star formation efficiency in early galaxies. The standard model assumes that galaxies convert gas into stars with a certain efficiency, calibrated by observations of the local and intermediate redshift universe. In the highly turbulent, high-pressure conditions of the very early universe, where gas densities were much higher and the intergalactic radiation field was more intense, the star formation efficiency might have been substantially higher than in later epochs. If galaxies in the first few 100 million years converted gas to stars 3 or 4 times more efficiently than local galaxies do, their stellar masses could accumulate faster than standard models predict. The efficiency argument is plausible, and some recent models incorporate it. The difficulty is that high star formation efficiency creates its own problems. Stars do not form quietly. Massive young stars emit intense ultraviolet radiation that heats and ionizes surrounding gas, and when they die in supernovae, the resulting blast waves drive gas out of the galaxy. This feedback process is thought to regulate and ultimately limit star formation efficiency. If early galaxies were forming stars at very high efficiency, the feedback should have been proportionally intense, and models need to explain why that feedback did not shut down the star formation that the efficiency was driving. This is not an impossible balancing act, but it requires the feedback physics in early galaxies to be calibrated in ways that current models do not fully capture. The third explanation involves the nature of dark matter. Standard cold dark matter, which moves slowly relative to the speed of light when it decouples from radiation in the early universe, produces the hierarchical structure formation described earlier. Small halos first, large halos later. Alternative dark matter models can modify this picture. Warm dark matter, which moves faster and therefore has a larger free streaming length that suppresses the formation of small-scale structures, would slow down the formation of small halos, which might seem to make the problem worse. But certain models of ultralight axion dark matter, sometimes called fuzzy dark matter, can have the opposite effect on star formation timescales in the specific ways galaxies cluster in the very early universe. Primordial black holes present a different dark matter, alternative with specific relevance to the early galaxy problem. Primordial black holes are hypothetical black holes formed not from stellar collapse, but from density fluctuations in the very early universe, during or shortly after inflation. If a significant fraction of dark matter consists of primordial black holes rather than fundamental particles, those black holes could seed galaxy formation much more efficiently than diffuse particle dark matter, because a massive compact object provides a gravitational seed around which gas can collapse more rapidly and more completely than around a diffuse halo. The primordial black hole hypothesis for galaxy seeds was proposed before Webb and has gained renewed interest from the Webb observations. A 2023 paper by researchers including Priyamvada Natarajan at Yale proposed that the early, compact, luminous objects Webb is seeing, including many of the little red dots, are consistent with being primordial black holes in the process of accreting gas and growing in the early universe, with the surrounding stellar component forming in their gravitational influence. The model remains speculative, but it connects the early galaxy problem with the early quasar problem in a way that a single mechanism, primordial black holes as seeds, could potentially resolve both. Early dark energy is a fourth explanation, primarily for the Hubble tension, but with implications for galaxy formation. In the standard CDM model, dark energy is constant. Lambda, the cosmological constant, contributes the same energy density at all times. Some researchers have proposed that dark energy was not constant, that there was an additional component of dark energy present in the early universe shortly before recombination that subsequently decayed away. This early dark energy would have changed the expansion history of the universe in the epoch before the CMB was emitted, altering the predicted CMB angular power spectrum in ways that would require a higher value of H0 to fit the Planck data. The early dark energy hypothesis makes the Planck measurement and the distance ladder measurement more compatible, but it introduces its own tensions. Fitting the CMB with early dark energy, while also matching baryon, acoustic oscillation observations and large scale structure measurements requires careful, fine tuning, and the model does not provide as clean a fit to all datasets simultaneously as standard CDM does. The Atacama Cosmology Telescope and the South Pole Telescope, 2mm wave observatories that have independently measured the CMB power spectrum, provide additional constraints, and early dark energy models face challenges fitting all of them simultaneously. Modified gravity theories offer a more radical departure. General relativity describes gravity on scales from the solar system to cosmological distances, and it does so with remarkable accuracy. But the extrapolation from solar system scales, where we have direct tests with centimetre precision, to cosmological scales, is an extrapolation of many orders of magnitude. Some modified gravity theories predict the same behaviour as general relativity in the solar system, but different behaviour at large scales or over cosmic time. If the gravitational interaction that governs structure formation in the early universe differs from what general relativity predicts, the rate of galaxy assembly could differ from CDM expectations. No compelling modified gravity theory has yet emerged that resolves both the Hubble tension and the early galaxy problem, while fitting all other cosmological observations. But the observation that two separate cosmological anomalies are both pointing toward the same early epoch suggests that if there is a modification to the standard model, it may be one that affects the physics of the universe's first billion years specifically. By the end of tonight, none of these explanations has achieved consensus. The field is in the stage of taking the anomalies seriously, generating a wide range of hypotheses and accumulating the additional data needed to distinguish between them. This is the scientific process operating on a timetable measured in years to decades, not in months. No one predicts that the stage of taking anomalies seriously and generating hypotheses would be the most intellectually productive moment in cosmology since the discovery of dark energy. But it is. There is another dimension of the early universe that Webb is revealing, one that connects intimately to the early galaxy problem but from a different angle, the epoch of rionization. The universe underwent a dramatic transition between approximately 150 million and 900 million years after the Big Bang. Before this epoch, the intergalactic medium, the gas filling the vast spaces between galaxies, was cold, neutral hydrogen. Neutral hydrogen is opaque to ultraviolet light. Any ultraviolet photons produced by the first stars would be absorbed before they could travel any significant distance. The universe was, in optical terms, foggy. The first stars burned in isolated pockets, unable to illuminate the larger cosmos through the surrounding neutral hydrogen fog. Then the first galaxies and quasars began producing enough ultraviolet radiation to ionize the neutral hydrogen around them. Ionization means stripping the electron from the hydrogen atom, leaving a bare proton. Ionized hydrogen, a proton, and a free electron is transparent to ultraviolet light. As the ionizing sources grew in number and luminosity, the ionization bubbles around individual galaxies expanded and eventually merged, and the intergalactic medium became progressively more transparent. By about 900 million years after the Big Bang, the reionization was complete, and the universe had cleared. The epoch of reionization is important for the JWST timeline problem because the efficiency and timing of reionization depends critically on the number, density, and luminosity of early galaxies. If there are more early galaxies than CDM predicted, or if they are more luminous than expected, they could drive reionization faster and earlier than standard models anticipated. The Webb observations are revealing exactly this: a surprisingly large number of bright, UV, luminous galaxies in the first 500 million years. Before Webb, models of reionization, constrained by Hubble observations, estimated that the galaxy population in the first 500 million years produced ionizing photons at a rate that allowed reionization to complete by the epoch we observe it completing, around 900 million years. The estimated number of galaxies was consistent with CDM predictions for the galaxy luminosity function, the distribution of how many galaxies there are at each luminosity. Webb has measured the galaxy luminosity function at redshifts above 9 with far greater precision and found that the bright end of the luminosity function, the number of the most luminous galaxies, exceeds CDM predictions by a factor of 10 to 100 at the highest redshifts. This is not a marginal excess. It is a large discrepancy at high significance. The bright end excess has several possible explanations. The most extensively discussed is that early galaxies have less dust than models assumed. Dust absorbs ultraviolet light efficiently, making galaxies fainter than they would be in the absence of dust. If early galaxies are more dust-free than later galaxies, they would appear brighter in UV, sensitive observations than models that assume typical dust fractions. Some evidence supports this interpretation. Spectroscopic observations of bright high, redshift galaxies do find lower dust content than typical galaxies at intermediate redshifts. But dust, free early galaxies do not fully account for the magnitude of the excess, especially at the highest redshifts. Another explanation, proposed by researchers including Charlotte Mason and colleagues, involves bursty star formation. In this picture, early galaxies form stars not at a constant rate, but in episodic bursts, periods of intense activity interspersed with periods of relative quiet. During a burst, a galaxy can briefly outshine its average luminosity by a large factor, making it temporarily much brighter than standard models based on steady, state star formation rates would predict. A population of galaxies all forming stars bursty rather than steadily would appear overluminous in snapshots like Webb images, because the snapshots preferentially capture galaxies during their bright phases. Bursty star formation is physically motivated. In the early universe, gas supplies could have been irregular and rapidly replenished by inflows along cosmic web filaments. The same feedback processes, supernova winds and radiation from young stars that regulate star formation in more quiescent later galaxies may have operated differently in the less settled environments of early cosmic history, producing more episodic rather than continuous star formation. The bursty star formation model is gaining traction, because it can simultaneously explain the excess of bright early galaxies, the scatter in the properties of high redshift galaxies, and some aspects of the reionization history. If galaxies were bursty, the times of peak brightness contributed disproportionately to ionizing photon production. The reionization history may have been more episodic and patchy than smooth models assumed. By the end of tonight, the reionization story is changing because of Webb in ways that flow directly from the early galaxy problem. If early galaxies are more numerous and more luminous than expected, they drove reionization faster and may have driven it more heterogeneously across the sky. High-fidelity maps of the patchy reionization history are now an active target of Webb observations, particularly through the 21-centimeter emission of neutral hydrogen, which will eventually be mapped by future facilities like the Square Kilometre Array. Tonight, the epoch of reionization is one of the best observational windows into the early galaxy problem, because the speed and efficiency of reionization directly encodes the properties of the galaxies that drove it. Every constraint Webb puts on the timing and patchiness of reionization is a constraint on the properties of the galaxies in the first billion years, and each of those constraints is tightening a test of the standard model from a different angle. The standard model is facing multiple tests simultaneously, and it is not failing all of them. But it is not passing all of them either, and the pattern of where it struggles is becoming more specific. A critical question runs through all the early galaxy discussion, and it deserves direct and sustained attention. How do we know these galaxies are actually at the distances claimed? How do we know the mass estimates are right? What if the entire galaxy problem dissolves when the measurements are done more carefully? This is exactly the right question to ask, and the answer, worked through honestly, explains why the community is taking the anomalies seriously rather than dismissing them. The primary tool for measuring the distance to a galaxy is spectroscopy. A spectrograph disperses light into its component wavelengths, like a very precise prism, and records the resulting spectrum. In the spectrum of a galaxy, you see emission lines, bright peaks at specific wavelengths produced when electrons in ionized atoms fall to lower energy states, and absorption lines, dark troughs at specific wavelengths where atoms absorb light at characteristic energies. The wavelengths of these lines are well established in laboratory physics. Hydrogen emits at 121.6 nanometers in the ultraviolet, the Lyman alpha line, oxygen at certain wavelengths, carbon, silicon. These wavelengths are constant set by quantum mechanics, the same in the most distant galaxy as in a laboratory on Earth. When you observe a galaxy at cosmological distances, the expansion of the universe has stretched these wavelengths. The Lyman alpha line, intrinsically at 121.6 nanometers, arrives at an observatory on Earth at a wavelength that is 1 plus z times its rest wavelength, where z is the redshift. A galaxy at z equals 11 has had its Lyman alpha line stretched from 121.6 nanometers to 1459 nanometers deep in the near infrared. This is precisely why Webb, with its exceptional infrared sensitivity, can measure spectroscopic redshifts of galaxies that Hubble, primarily an optical and ultraviolet telescope, could not. Webb's near-spec instrument, the near-infrared spectrograph, is the workhorse for spectroscopic confirmation of high redshift galaxies. It can measure spectra of up to 100 objects simultaneously using micro-shutter arrays, tiny electronically controlled windows that open to admit light from selected targets. When NearSpec observes a high redshift galaxy and the Lyman alpha line is detected at the expected shifted wavelength, the redshift is confirmed. When additional spectral features, emission lines from oxygen, carbon, or other elements, are also detected at the correspondingly shifted wavelengths, and they all agree on the same redshift, the confirmation is airtight. For JADES, GS, Z-photonin, 0, the spectroscopic confirmation at Z equals 1432 was based on multiple detected features. The Lyman break, a sharp drop in flux below the Lyman, alpha wavelength caused by neutral hydrogen in and around the galaxy, absorbing photons blueward of Lyman, alpha was clearly detected. Emission lines from oxygen were detected at the wavelengths consistent with Z equals 14.32. Multiple independent features all pointed to the same redshift. This is not an uncertain photometric estimate, it is a spectroscopically confirmed measurement. The stellar mass estimate is a different and independently uncertain inference. Estimating stellar mass requires fitting the galaxy's spectral energy distribution, its brightness at multiple wavelengths, to models of stellar populations of different ages, initial mass functions and dust contents. The fit gives the combination of stellar masses, ages and dust that best reproduces the observed brightness profile. This inference depends on assumptions about stellar physics that are calibrated on nearby galaxies and may not hold perfectly in the extreme conditions of very early galaxies. However, the uncertainty in stellar mass estimation has been studied extensively. The systematic errors are significant but bounded. The most commonly cited concern is that the initial mass function, the distribution of stellar masses produced per star formation event, may be different in early galaxies than in local ones. If early galaxies produced more high mass stars relative to low mass stars than local galaxies do, the ratio of light to stellar mass would be different, and the mass estimates would need to be revised. The direction of this uncertainty is such that it typically works to reduce the mass estimates if early galaxies were more top-heavy in their stellar populations. Even accounting for this uncertainty, the most massive early galaxies found by Webb remain at or above the upper limits predicted by standard CDM simulations. The most robust way to test whether the stellar mass problem is real is to look at it statistically. A single galaxy might be a measurement outlier. A large sample of galaxies at high redshift, all showing stellar masses exceeding the standard model predictions by similar amounts, is much harder to explain as a statistical fluke. The JD's survey and the Sears survey, the Cosmic Evolution Early Release Science survey, have produced samples of dozens of galaxies at redshifts above 8, with stellar mass constraints, and the distribution of those masses consistently falls above what the illustrious TNG simulation, the state-of-the-art in CDM galaxy formation modelling, predicts. A 2023 paper by Lab and colleagues, analysing a sample of Webb, discovered early galaxies, estimated that 6 of them had stellar masses exceeding 10 billion solar masses at redshifts above 7 to 8. The standard model was not expected to produce galaxies of that mass until significantly later epochs. These estimates were refined and partly revised downward in subsequent work, but even under the most conservative mass estimates, a statistically significant excess at the high mass end remained. Tonight, the confidence in the early galaxy problem comes not from a single spectacular object, but from the intersection of photometric surveys, spectroscopic confirmation, stellar mass estimates, and comparison with theoretical predictions. Each link in that chain has its uncertainties, but the uncertainties have been studied carefully. They have been reduced over the 3 years since Webb began operations, and the residual tension with the standard model has not disappeared. No one expects the most precise cosmological observations in history to produce systematic effects large enough to explain away a statistically significant excess in galaxy masses at high redshift. But the community continues to test that possibility carefully, and will continue to do so. The black hole problem in the early universe is worth examining on its own terms, because it connects the early galaxy problem to a separate and independently motivated observational challenge that predates Webb by nearly 2 decades. The discovery of quasars at high redshift, before Webb launched, already represented a puzzle for standard formation models. The most distant quasar known before Webb was confirmed at redshift 7.5, meaning it was observed when the universe was approximately 680 million years old. This quasar, catalogued as ULAS J1342+0228, contains a central black hole with a mass of approximately 800 million solar masses. 800 million solar masses of black hole in 680 million years. Growing a black hole to that mass in that time requires the black hole to accrete material at very close to its theoretical maximum rate, the Eddington luminosity limit, essentially continuously from birth. Any interruption in the accretion, any period of sub-Eddington growth, leaves the black hole too small at the end of 680 million years, unless it started from a very massive seed. The seed mass problem is at the heart of the high redshift black hole puzzle. Black holes in the local universe form in two well understood ways. Stellar mass black holes, with masses between roughly 3 and 100 solar masses, form from the collapse of massive stars at the ends of their lives. Supermassive black holes, with masses from millions to billions of solar masses, are found at the centres of essentially all massive galaxies. The path from a stellar mass black hole seed to a billion solar mass supermassive black hole in less than 700 million years requires sustained maximum accretion for the entire period, which is physically challenging. The radiation produced by the accreting material tends to push surrounding gas away, limiting the accretion rate. Standard models of black hole growth typically produce seeds of at most a few tens of solar masses from stellar remnants, or up to perhaps 100,000 solar masses from the direct collapse of massive gas clouds in the early universe. Neither of these provides a comfortable seed for growing to 800 million solar masses in 680 million years. Webb has found black holes in galaxies at even higher redshifts, including the active nucleus detected in GN, Z11 at redshift 10.96. The black hole mass in GN, Z11 is less certain, estimated at roughly 1.6 million solar masses, which is smaller than the extreme quasar black holes, but still substantial given the available growth time of approximately 430 million years. More striking are the broader population of compact red luminous objects that Webb has found in the first billion years. These objects, the little red dots, show spectroscopic features consistent with active galactic nuclei, meaning accreting black holes in galaxies that appear compact and reddened. The spatial density of these little red dots exceeds what standard models of black hole formation predict for that epoch by a significant margin. The primordial black hole hypothesis, as mentioned earlier, provides one way to connect the early galaxy and early black hole problems. If some fraction of dark matter consists of primordial black holes formed during inflation or shortly after, those black holes could serve as the seeds around which early galaxies assemble, and as the seeds for the central supermassive black holes that quasars illuminate. The seed masses available would be much larger than stellar remnants, and could potentially allow the observed quasar black holes to grow from their seeds without requiring continuous maximum rate accretion. No one predicts that primordial black holes, a hypothetical population proposed initially in the 1960s by Stephen Hawking and collaborators as a possible solution to the dark matter problem, would resurface as a candidate explanation for early galaxy formation and early supermassive black hole growth simultaneously. But the multi-way connection between the early galaxy masses, the early black hole masses, and a dark matter component consisting of compact objects is becoming a coherent alternative narrative that several research groups are developing in parallel. An alternative black hole seed model, called direct collapse black holes, proposes that in certain environments in the early universe, massive gas clouds can collapse directly into black holes of 50 to 100,000 solar masses without ever forming stars. For direct collapse to work, the gas needs to cool slowly, which requires the absence of molecular hydrogen, which in turn requires intense ultraviolet radiation from a nearby star, forming regions to dissociate the hydrogen molecules. The conditions needed: a dense gas cloud in the vicinity of a massive star, forming galaxy but not so close that the star formation feedback disrupts the cloud before collapse, are specific and rare. But if direct collapse occurred even rarely in the early universe, the resulting black holes would be massive enough to grow to quasar sizes by z=7 without requiring implausibly sustained accretion. Webb's ability to detect the spectroscopic signatures of active nuclei in early galaxies is now providing the first real constraints on the seed populations. If the little red dots are direct, collapsed black holes in the process of assembling their first stellar populations, their distribution in mass, luminosity, and spatial density should follow predictions from direct collapse models. Early analyses are promising but not conclusive. Tonight, the black hole timeline problem and the galaxy timeline problem are not separate anomalies. They are two aspects of a single question. In the first billion years of the universe, how did the first massive structures, whether galaxies or black holes, assemble faster than our models expected? The answer will come from more Webb observations, from the Roman Space Telescope expected to launch in the late 2020s, and from the theoretical work being done now to identify which modifications to the standard framework are consistent with all of the available evidence simultaneously. The theoretical response to the Webb observations has been substantial, and it is worth spending time on what the simulations say and how they are being revised, because this is where the science is actively being made. Galaxy formation simulations are among the most computationally intensive projects in physics. They require modelling the gravitational evolution of hundreds of millions of particles of dark matter and ordinary matter simultaneously, on timescales ranging from the microseconds of individual supernova events to the billions of years of cosmic evolution, across spatial scales ranging from individual molecular clouds to clusters of galaxies many millions of light years across. The mismatch of scales is the central challenge. The processes that regulate star formation happen on scales of a few light years inside individual molecular clouds, but the environment those clouds form in is shaped by cosmological processes operating on scales of hundreds of millions of light years. The dominant simulation frameworks before Webb included Illustris, Illustris TNG, Eagle, and Fire, each implementing somewhat different prescriptions for the grid physics, the small-scale processes that cannot be resolved directly, but must be approximated with analytic recipes. In Illustris TNG, for instance, star formation occurs in gas cells that meet certain density thresholds. Supernova feedback is implemented as thermal and kinetic energy injection into surrounding gas, and black hole feedback is modelled through two modes: quasar, mode at high accretion rates, and radio, mode at low accretion rates, with parameters calibrated to reproduce the properties of galaxies at intermediate redshifts. The problem with these calibrations is that they were done primarily on observations of the universe at redshifts below 3, where the bulk of the galaxy population is accessible to pre-Webb surveys. Extrapolating these calibrated prescriptions to the universe at redshifts above 10 is a significant extrapolation, and the Webb observations are revealing that the extrapolation fails. The most direct way to see this is to compare the galaxy stellar mass function, the number of galaxies per unit volume at each stellar mass, as predicted by Illustris TNG at redshifts above 8, with the galaxy stellar mass function as measured by Webb. The comparison shows that Illustris TNG under predicts the number of high-mass galaxies at high redshift by factors of 10 to 100. This is not a marginal discrepancy at the edge of the prediction. It is a large gap in a region the simulation should, if its physics is right, reproduce. The community's response has followed two paths. The first is to modify the simulations to find prescriptions that reproduce the Webb observations. The second is to understand, theoretically, what changes in the early universe could produce the observed galaxy population, and then encode those changes in the simulations. The modifications being explored include reducing supernova feedback efficiency in early galaxies, on the grounds that the early intergalactic medium may have been denser and more confining, making it harder for supernova-driven winds to escape, and thereby keeping more gas available for star formation. They include allowing higher star formation efficiencies in high-density environments, directly encoding the possibility that early dense conditions promoted faster gas, to star conversion. They include varying the initial mass function to be more top, heavy in early galaxies, producing more high mass stars per unit mass of gas, and therefore more luminosity per unit stellar mass. A 2023 study by a team including Mark Vogelsberger at MIT, one of the architects of the Illustris simulation, specifically explored modifications to the Illustris TNG framework to reproduce the Webb bright end excess. The study found that a combination of reduced dust content in early galaxies and episodic star formation, with bursts separated by quiescent phases, could bring simulation predictions into better agreement with Webb observations without requiring fundamental changes to the cosmological framework. This is reassuring in one sense. The standard framework may not need to be discarded, only calibrated differently at high redshift. But it is also informative in a deeper sense. The calibrations that worked for nearby galaxies do not work for early ones, which means the physics of galaxy formation in the early universe is genuinely different from what we modelled. The fire simulations, which simulate individual galaxies at much higher resolution than volume, filling simulations like Illustris TNG, have been applied to specific high redshift galaxies identified by Webb. The fire models naturally produce bursty star formation at high redshift, because they resolve the individual molecular cloud scales where star formation occurs and where feedback operates. The resulting burst and quench cycles produce luminosity variations that look qualitatively similar to what is observed in early Webb galaxies. This is a point of convergence between the observational and theoretical communities. What the simulations are not yet producing is a full explanation for the most extreme outliers, the galaxies with the highest stellar masses at the earliest epochs, the ones that are not just above the median Illustris TNG prediction, but above the extreme high end of the prediction. For these objects, modifications to feedback and star formation efficiency alone may not be sufficient, and the cosmological context, perhaps a higher than CDM, predicted amplitude of density fluctuations on small scales in the very early universe, may need to change. This points towards something deeper in the model. CDM predicts a specific spectrum of density fluctuations from inflation, characterized by a nearly scale invariant power spectrum. If the actual power spectrum of primordial fluctuations was slightly more enhanced on small scales than the standard inflation prediction, structure would form earlier and more abundantly in the early universe, potentially explaining the early galaxy excess without requiring modifications to star formation or feedback physics. This is a testable prediction. The CMB power spectrum at very small angular scales, probed by ground-based millimeter telescopes, constrains the primordial power spectrum, and future measurements will tighten those constraints. By the end of tonight, the simulations are in an active phase of revision. They are being run with modified prescriptions and compared with Webb data in iterative cycles. This is the scientific process functioning correctly. Observations constrain models, models are revised models make new predictions, and new observations test them. The timeline for resolution is years to a decade, not months. No one predicts that a revision of galaxy formation simulations would be scientifically productive. Every revision is productive precisely because it improves the model's fidelity to the universe it describes. The tension revealed by Webb will be tested and hopefully resolved by the next generation of observatories, several of which are now under construction or in advanced development. Understanding what those facilities will add to the picture is important context for where cosmology is heading. The Nancy Grace Roman Space Telescope, named after NASA's first chief of astronomy, is designed as a wide field complement to Webb. Where Webb has a comparatively narrow field of view but extraordinary depth and sensitivity, Roman will have a field of view roughly 100 times larger than Webb's NIRCam, while maintaining comparable infrared sensitivity. Roman is currently scheduled to launch in the late 2020s and will conduct large area surveys of the sky in infrared light, discovering hundreds of thousands of galaxies at high redshift that Webb's targeted observations are finding one patch at a time. Roman's contribution to the early galaxy problem will be primarily statistical. The tension with CDM at the high mass end of the galaxy mass function requires large samples to characterize precisely Because the most massive rare galaxies are rare by definition, you need to survey large volumes to find them. Roman's wide field means it will build up the sample of high, redshift galaxies dramatically, allowing precise measurements of the galaxy mass function at redshifts above 7 and 8, with sample sizes of thousands rather than dozens. If the tension with the standard model is real and systematic rather than a product of small, number statistics in Webb's early samples, Roman will confirm and quantify it precisely. Roman will also conduct what may become the definitive survey of Type Ia supernovae for cosmology, potentially resolving or deepening the Hubble tension. By measuring thousands of high redshift supernovae with unprecedented precision, Roman will either confirm the Chasles value of R0 or introduce enough new constraints to reveal where the systematic errors lie in either the early or late universe measurements. On the ground, 3 extremely large telescopes are under construction in Chile's Atacama Desert, the driest and highest altitude site available for astronomical observations in the Southern Hemisphere. The extremely large telescope being built by the European Southern Observatory will have a segmented primary mirror 128 feet across, making it the largest optical and near-infrared telescope ever built. Its light gathering area will exceed all existing optical telescopes combined. Its instruments, particularly the high-resolution spectrograph and the adaptive optics camera, will allow detailed chemical and kinematic studies of individual stars in nearby early-type galaxies, and of the gas dynamics in high redshift galaxies discovered by Webb and Roman. The 30-meter telescope, planned for Mauna Kea in Hawaii, though facing ongoing permitting challenges, and the giant Magellan telescope being built at Las Campanas Observatory in Chile, will provide similar capabilities with slightly different instrument suites and observational complementarities. Tonight, the extremely large telescopes will contribute something Webb cannot: spectroscopy at very high spectral resolution. Webb's NERSpec has a spectral resolution sufficient to measure redshifts and detect individual emission lines, but not sufficient to measure the precise velocities of stars within a galaxy, which would reveal the galaxy's dynamical mass, how much mass is actually present and holding the galaxy together gravitationally, independently of the stellar population modelling used for photometric mass estimates. If the dynamical masses of early Webb galaxies are confirmed to be as large as the stellar population estimates suggest, the case for a tension with the standard model becomes stronger. If the dynamical masses are smaller, that would suggest the stellar population models are over-predicting the stellar mass. The Square Kilometre Array is a radio telescope array being built in Australia and South Africa with a total collecting area of roughly 1 million square feet, distributed across thousands of individual antennas. Its primary science targets include mapping the 21 centimetre emission of neutral hydrogen through the epoch of reionization, the cosmic dawn, and the dark ages, filling in the observational gap between what Webb can see and the cosmic microwave background. The SKA's 21 centimetre maps of the reionization epoch will provide direct observational constraints on when and how quickly the universe went from neutral to ionized, testing the galaxy luminosity functions Webb is measuring against the reionization history they must produce. The Rubin Observatory, also known as the Vera Rubin Observatory, in honour of the astronomer who discovered the rotation curve evidence for dark matter, is a ground-based wide field optical telescope in Chile that will conduct the legacy survey of space and time, a 10-year survey of the entire southern sky every few nights. Rubin will discover tens of billions of objects, including hundreds of millions of galaxies, and will constrain the large-scale structure of the universe at intermediate redshifts with unprecedented precision. Its contribution to the Hubble tension comes through baryon acoustic oscillation measurements in the galaxy distribution, which provide an independent standard ruler for measuring cosmic distances without the distance ladder. The combination of Roman for wide, field-high redshift galaxy surveys, Webb for targeted, deep spectroscopy of individual objects, the extremely large telescopes for high, resolution ground-based spectroscopy, the SKA for 21, centimeter ionization mapping, and Rubin for large-scale structure and supernovae will constitute the most comprehensive cosmological observational program in history. Together, these facilities will either resolve the tensions Webb has revealed or sharpen them to the point where the solution becomes clear. No one predicts that the decade of the 2030s will leave cosmology unchanged. The data quality and quantity arriving from these facilities will be qualitatively different from anything available before, and the theoretical models will need to match them precisely rather than approximately. That precision will either confirm that the CDM framework, with modest modifications, accounts for everything we observe, or it will reveal specific, well-characterized failures that point toward the new physics we need to look for. Both outcomes are worth looking forward to. If the model survives, we will know it more deeply than we do now. If it needs revision, we will finally have the evidence to understand how to revise it. There is a perspective on the JWST timeline problem that becomes available when you step back from the specific numbers and ask the larger historical question. How often has our best model of the universe turned out to be incomplete? And what did we learn from the revisions? The answer is that cosmology has been revised at the deepest level several times in the last century, and each revision followed a pattern that the current situation resembles closely. In the 1920s, most astronomers believed the Milky Way was the entire universe. The nebulae, fuzzy patches of light seen through telescopes, were assumed to be nearby gas clouds within or just beyond the Milky Way. Heber Curtis argued they were distant independent galaxies. Harlow Shapley argued they were not. The debate was settled when Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson in California to identify Cepheid variable stars in the Andromeda Nebula and measure its distance at about 900,000 light-years, placing it far beyond the Milky Way. The universe was, instantly, vastly larger than it had been. In the late 1920s and 1930s, after Hubble's measurement of cosmic expansion, the dominant cosmological model was still the steady-state model, first formalized by Fred Hoyle, Hermann Bondi, and Thomas Gold in 1948. In the steady-state model, the universe had no beginning. It was eternal and unchanging in its large-scale properties. As galaxies moved apart from each other due to expansion, new matter was continuously created to maintain a constant density. The universe looked the same at all times and from all places. The steady-state model was overthrown not by a single dramatic observation, but by the accumulation of evidence that the universe had evolved over time, the discovery that distant galaxies looked different from nearby ones, suggesting they had changed over cosmic history, the discovery of quasars at high redshift, luminous objects that no longer existed in the nearby universe, and most definitively, the discovery of the cosmic microwave background by Arno Penzias and Robert Wilson at Bell Labs in 1965. The cosmic microwave background was the thermal afterglow predicted by the Big Bang model, the remnant heat of the hot, dense early universe. Its detection settled the debate between steady state and Big Bang definitively in favour of the Big Bang. In the 1990s, cosmologists believed the expansion of the universe was slowing down. The universe was dominated by matter, and gravity pulling matter together should have been decelerating the expansion over time. Two independent teams, the High Z Supernova Search Team and the Supernova Cosmology Project, measured the distances to distant Type Ia supernovae to determine how the expansion rate had changed. No one expected both teams to independently find the same surprising result. The expansion was not slowing, it was accelerating. The discovery of the accelerating expansion, announced in 1998 and awarded the Nobel Prize in Physics in 2011, required the introduction of dark energy into the cosmological model, a form of energy intrinsic to space itself that exerts a repulsive gravitational effect, driving the accelerating expansion. CDM was born as the complete model, incorporating dark matter for structure formation and dark energy for the late time acceleration. Each of these revisions followed the same pattern. A well-established model, trusted because it explained a large body of existing observations, encountered new observations that it could not accommodate. At first, the new observations were questioned. Were the measurements right? Were there systematic errors? Could the existing model be adjusted to accommodate them? Over time, as the observations were confirmed by independent groups using different methods, the case for a genuine incompleteness in the model became undeniable. The revision was made, and the new model explained both the old observations and the new ones in a unified framework. Tonight, the JWST observations are at an early stage of this pattern. The measurements are being confirmed, the systematic errors are being studied carefully, and the theoretical community is generating potential explanations. The case for a genuine incompleteness in CDM's account of the first billion years is building, but it has not yet reached the point where a specific revision is clearly favoured. What history suggests is that the resolution will not require discarding CDM. The steady-state model was replaced because it was fundamentally wrong about the universe's history. CDM is not fundamentally wrong. It correctly predicts the CMB, the large-scale structure, the baryon acoustic oscillations, the abundance of light elements, and dozens of other observational constraints. What is being tested is the model's account of a specific and underobserved period, the first billion years, where the predictions were made by extrapolating prescriptions calibrated on more accessible epochs. The revision, when it comes, will likely look like what happened with dark energy, an additional ingredient, or a more careful specification of how existing ingredients behave in extreme early conditions will be identified and incorporated. The model will become richer and more accurate. The observations that prompted the revision will become its confirmations. No one predicts exactly what that additional ingredient will be. That is what makes the current moment in cosmology genuinely exciting rather than genuinely alarming. The alarm would be appropriate if the anomalies pointed toward inconsistencies in the foundations of the model, in general relativity or quantum field theory, or the fundamental physics of the Big Bang itself. They do not obviously do that. They point toward details of how structure assembled in the early universe, details that were underspecified before Webb gave us the data to specify them. By the end of tonight, the JWST timeline problem is best understood not as a crisis for cosmology, but as cosmology reaching the next level of precision. The universe has more detail in its early history than our model had captured. Webb is providing that detail. The model will be updated to accommodate it, and the updated model will be a more accurate description of how the universe actually evolved from its beginning to the present. That is how science is supposed to work. It is working that way, and we get to watch. Tonight, there is a piece of the early galaxy problem that connects the Webb observations to the very deepest questions of stellar physics, and it is worth dwelling on because it illustrates how the galaxy timeline problem is not just a count of galaxies, but a question about the physical processes that build them. Stars are not all the same. The night sky as visible from Earth shows stars ranging from the bright bluish-white of Sirius and Rigel to the cool deep red of Betelgeuse and Antares. These colours reflect real differences in surface temperature, which in turn reflect real differences in mass, age, and chemical composition. But the most fundamental distinction in stellar population science is not between blue stars and red stars. It is between stars born early in the universe's history, when the available material was almost pure hydrogen and helium, and stars born later, when successive generations of stellar evolution had enriched the interstellar medium with heavier elements. Astronomers call these populations Pop-A, Pop-2, and the hypothetical Pop-3. Population domain stars are young, metal, rich stars like the Sun, formed from interstellar material that has been processed through many generations of stellar nucleosynthesis. The Milky Way's disk is dominated by population 1 stars. Population 2 stars are old, metal, poor stars found in the bulge, halo, and globular clusters of galaxies, formed early in the galaxy's history when the available heavy element abundance was low, and population 3 stars are the theoretical first generation, metal-free, formed entirely from the primordial hydrogen and helium of the Big Bang, and expected to have been massive, short-lived, and of decisive importance to the subsequent evolution of the universe. No population 3 star has ever been directly observed. They are expected to have been so massive that they burned through their fuel in a few million years and died in supernova explosions before any of our current instruments could detect them, even in principle. What we can observe are the chemical signatures of their deaths in the most metal-poor stars, the ancient survivors of early stellar generations in the halos of the Milky Way and nearby galaxies. The metal-poor stars in the Milky Way's halo carry in their atmospheres the chemical fingerprints of the first stellar generations. By analysing the abundance ratios of different elements in these ancient stars, astronomers can work backward to understand what kind of stars produce those elements. The pattern of carbon, nitrogen, oxygen, magnesium, silicon and iron at extremely low overall metallicity encodes information about the stellar masses and explosion mechanisms of population 3 supernovae. This field, called stellar archaeology, has produced constraints on the typical masses of population 3 stars that are broadly consistent with theoretical models, massive, perhaps tens to hundreds of solar masses, and leaving behind both chemical enrichment and massive remnant black holes. The population 3 stars are directly relevant to the JWST timeline problem because if the first stellar generation was systematically more massive than later generations, the ratio of stellar luminosity to stellar mass was dramatically different in the very early universe. A population 3 star of 100 solar masses is hundreds of thousands of times more luminous than the Sun. Its luminosity per unit mass is perhaps 1,000 times higher than for a Sun-like star. If early galaxies had higher fractions of massive population 3 or massive early population 2 stars, their luminosities would be much higher per unit stellar mass than models calibrated on the local universe would predict. This connects directly to the bright end excess in the Webb galaxy luminosity function. Some of the apparent excess of bright early galaxies may not reflect higher stellar masses, but higher luminosity per unit stellar mass, because the initial mass function was more top-heavy, producing more of the massive luminous stars per unit of gas converted to stars than later epochs of galaxy formation. Under this interpretation, the stellar mass problem partially dissolves. The galaxies are less massive than their luminosities imply, but they are more luminous per unit mass because of an unusually top-heavy stellar population. No one expects the initial mass function to be constant across all environments and all cosmic epochs. The physics of the initial mass function is still not fully understood even in the local universe. The Jeans mass, which sets the characteristic scale for gravitational instability in a gas cloud, and thus the characteristic stellar mass that forms, depends on the temperature and density of the gas. In the early universe, gas was hotter relative to later epochs because of residual heating from the epoch of rionization and because the cosmic microwave background, which permeates all of space, was warmer at high redshift, providing a radiation floor that kept gas temperatures higher than in the modern universe. Higher gas temperatures imply higher Jeans masses, meaning the characteristic mass of stars formed from the gas should have been larger. A top-heavy initial mass function in the early universe is physically motivated by these conditions. Whether the top-heavy initial mass function effect is large enough to fully explain the Webb bright end excess is an active research question. The most extreme proposals, initial mass functions where essentially all stars are massive, are inconsistent with the chemical enrichment patterns observed in metal, poor halo stars. If early stars were all massive, the abundance ratio patterns they would produce differ from what is actually observed. A moderately top-heavy initial mass function, with more massive stars but still including lower mass stars, is consistent with stellar archaeology constraints and may be sufficient to reduce the tension with the standard model. The connection between stellar populations and the JWST timeline problem also runs through what Webb can actually observe spectroscopically in high redshift galaxies. The emission lines that NIRSpec detects in early galaxies, particularly the Balmer lines of hydrogen and forbidden lines of oxygen and nitrogen, are produced by gas ionized by the ultraviolet radiation of young massive stars. The ratios of these emission lines encode information about the ionization state of the gas, the temperature of the ionizing radiation field, and the chemical composition of the gas. Early Webb spectra of high redshift galaxies show emission line ratios that differ systematically from those of nearby stars, forming galaxies in ways consistent with hotter, more massive stellar populations. Tonight, the stellar population story is a reminder that the JWST timeline problem is not just a problem about galaxies as objects. It is a problem about the physics of star formation in extreme environments. The first billion years of the universe provided conditions for star formation that are not replicated in the present universe, and calibrations of galaxy formation models developed on present-day or intermediate redshift observations may simply not capture the physics of that early extreme era. The resolution of the timeline problem may be, in part, a resolution of the stellar population problem, an understanding of how stars form differently in the first billion years, and how that different formation mode explains the galaxies Webb is finding. We are still in the early stages of that understanding. The combination of Webb spectroscopy, stellar archaeology in the Milky Way's halo, and the theoretical modelling of population 3 star formation is converging on a more detailed picture of how the first stellar populations formed and how they shape the galaxies that followed. That picture is not yet complete, but it is sharper than it was before Webb launched, and it will continue to sharpen with each year of observations and each new generation of instruments brought to bear on the question. But the combination of spectroscopy from Webb, chemical constraints from stellar archaeology, theoretical models of early star formation, and future high resolution observations from extremely large telescopes is building toward a comprehensive picture of how the first stellar populations shaped the first galaxies and how those galaxies shaped the universe that followed. There is a structural context for the early galaxy problem that we have mentioned but not fully examined. The cosmic web. The large-scale structure of the universe, the pattern of filaments, sheets, voids, and clusters within which all galaxies are embedded, is not a background feature of the cosmological story. It is an active participant in the JWST timeline problem, because the rate at which matter concentrated into galaxies in the first billion years depended critically on where within the cosmic web that matter was located. The cosmic web is the product of the same gravitational instability that built the first galaxies, but operating at scales of tens to hundreds of millions of light years rather than the scales of individual galaxies. The primordial density fluctuations seeded by inflation were not random noise. They had a specific statistical character, described by what cosmologists call the power spectrum, which encodes how much fluctuation power there was at each scale. On the largest scales, fluctuations were small. On smaller scales, they were progressively larger. The first structures to collapse were therefore small halos, which then merged into progressively larger ones, a hierarchical process that produces the filamentary web we observe. By the time Webb is observing at redshifts above 10, the cosmic web has been assembling for several 100 million years. The first filaments have formed, and the intersections of filaments, the cosmic web's dense nodes, are where the first cluster, like overdensities, are beginning to coalesce. These are exactly the places where early galaxy formation should be concentrated. No one predicts, from first principles, exactly how concentrated early galaxy formation should be in the densest nodes of the cosmic web at high redshift. The standard model makes predictions about the average properties of the galaxy population at a given redshift, but the spatial distribution of those galaxies, the degree to which they cluster in the densest environments, depends on the interplay between dark matter halo formation rates and the galaxy formation processes within those halos, Webb has begun providing the first observational maps of the cosmic web at high redshift. The JWST Primer survey and the JADES survey have identified clusters over densities of high redshift galaxies that are the progenitors of the massive galaxy clusters we observe in the nearby universe. Some of these clusters contain surprisingly large numbers of massive galaxies in small regions of space, suggesting that the densest environments in the early universe were forming galaxies at rates even higher than average high redshift galaxies, amplifying the tension with the standard model. The cluster problem is distinct from but related to the average galaxy mass function problem. Even if the average galaxy population at a given redshift is in modest tension with the standard model, an overdense cluster region could contain galaxies that are individually more massive and collectively more numerous than any random region of the universe at that epoch. Clusters represent the extreme tail of the density distribution, and they evolve faster than average density regions because the higher dark matter density means gravity is stronger and structures collapse sooner. The discovery of clusters containing multiple massive galaxies at redshifts above 8 is telling us that the most extreme overdensities in the early universe were even more productive at forming galaxies than the standard model expected. This could reflect the same underlying causes as the average galaxy mass problem, whether enhanced star formation efficiency, a more heavy initial mass function, or reduced feedback, but amplified by the high density environment. Or it could reflect a separate issue with how the standard model handles the tail of the density distribution, the statistics of extreme cosmic environments. Webb's contribution to the cosmic web story goes beyond finding clusters. It is mapping the intergalactic medium between galaxies at high redshift, tracing the gas that links individual galaxies along cosmic filaments. The ultraviolet spectra of distant quasars, observed through the intervening universe, carry absorption line signatures of neutral hydrogen and heavy elements in the intergalactic medium. Webb's sensitivity allows it to trace these absorption systems to higher redshifts and with greater sensitivity than before, building up a three-dimensional picture of where gas is concentrated and where it is dilute at cosmic dawn. The intergalactic medium at high redshift is not a passive background. It is the reservoir from which galaxies draw their fuel for star formation. Gas flows along cosmic filaments into dark matter, halos, cools, and forms stars. The rate at which this fuel supply arrives determines, at least partly, how fast galaxies can grow. If the filaments in the early universe were denser or more efficiently channeling gas into halos than standard models assumed, early galaxies would have had access to more fuel earlier, and their stellar masses could have grown faster. Some simulations have begun exploring this possibility, finding that the gas accretion rates along filaments in the early universe, where the intergalactic medium was denser and more metal-poor, may have been substantially higher than at later epochs. High accretion rates combined with high star formation efficiency produce stellar mass growth rates that better match the Webb observations without requiring dramatic changes to the fundamental cosmological framework. Tonight, the cosmic web provides a reminder that no galaxy exists in isolation. Every galaxy is embedded in a larger structure that modulates its access to gas, its rate of mergers with other galaxies, and the radiation environment in which its stars form. The cosmic web at high redshift was a different kind of web than the one we observe today. Denser, more turbulent, with higher accretion rates and more frequent mergers. Understanding how that environment shaped the first galaxies is as important as understanding the internal physics of those galaxies themselves. Webb is providing, for the first time, the observations needed to map that environment directly at the epochs where the timeline problem is concentrated. The combination of galaxy spectroscopy, intergalactic medium tomography, through quasar absorption lines, and cluster mapping will, over the next several years, build a picture of the early cosmic web that can be compared directly with simulations. That comparison will either confirm that the simulations suitably modified reproduce the early universe, or it will reveal the specific environmental features that the models are missing. No one predicts that a telescope designed to observe the atmospheres of nearby exoplanets and the birth of stars in nearby nebulae would simultaneously provide the most detailed maps of the cosmic web at the dawn of galaxy formation. But Webb's capabilities are broad enough to do all of these things, and each observation, in its way, contributes to the same fundamental question. The JWST timeline problem is really asking, in the most extreme conditions that have ever existed for galaxy formation, what actually happened? That question is now, for the first time, becoming answerable from observation rather than from theory alone. Let us return to where we started, because everything we have covered tonight points toward a single and genuinely exciting conclusion. We began with a telescope floating 1 million miles from Earth, pointing mirrors the size of a tennis court at the oldest light in the cosmos. We began with a model, Lambda Cold Dark Matter, that had taken 30 years of observations to build, and that described the evolution of the universe with extraordinary precision across almost every scale and epoch it had been tested on. And we began with the unexpected. The first images from Webb showing structures in the very early universe that the model did not predict. Tonight, we traced what those structures are. We found galaxies at redshifts above 14, spectroscopically confirmed, their distances measured with the same atomic physics that governs every spectrum in every laboratory on Earth. We found stellar masses in these galaxies exceeding what the standard model expected to have assembled so early in cosmic history. We found chemical enrichment, the presence of oxygen and other elements heavier than helium in galaxies only 290 million years old, requiring at least one prior generation of massive stars to have already lived and died. We found active black holes in early galaxies, millions and billions of solar masses already assembled, challenging standard models of black hole growth just as the galaxies challenge standard models of galaxy formation. Tonight, we explored the Hubble tension and found that the universe's current expansion rate, measured two ways by two independent and carefully controlled methods, gives two different answers to level of discrepancy that cannot be explained by measurement errors alone. The early universe Planck measurement and the late universe distance ladder measurements disagree at more than 5 standard deviations, and Webb's contributions to the tension have deepened rather than resolved it. We sat with the explanations, modified stellar mass estimation, enhanced early star formation efficiency, bursty star formation, early dark energy, primordial black holes as structure seeds, modifications to the primordial power spectrum. None of them has achieved consensus. Several of them are being actively tested. The tests will continue for years, and we trace the theoretical response, simulation frameworks being revised, new prescriptions for feedback and star formation efficiency being encoded, new runs being compared with Webb data in iterative cycles. The simulations are getting better. The model is being refined rather than discarded. By the end of tonight, what this all amounts to is something genuinely important to hold. The standard model of cosmology is not wrong. It correctly predicts the abundances of light elements produced in the Big Bang. It correctly predicts the temperature fluctuations of the cosmic microwave background. It correctly predicts the large-scale distribution of galaxies across the observable universe. It correctly predicts the existence and properties of dark matter and dark energy. These are not small successes. They are the predictions of a model that has been tested against the observable universe on extraordinary scales and has passed those tests with quantitative precision. What the Webb observations are telling us is that the model's account of the first billion years, the specific processes by which the first galaxies and black holes assembled, may be incomplete in ways that require refinement. The refinement might be modest, adjustments to how we model star formation efficiency and feedback in the extreme conditions of the early universe. Or it might be more substantial, a modification to the primordial power spectrum of density fluctuations, or the introduction of new physics in the dark matter sector, or the discovery that early dark energy affected the universe in ways not captured by the standard treatment. We do not know yet which category the refinement belongs to. What we do know is that Webb is giving us the data to find out, and that the data it is producing is the highest quality view of the early universe humanity has ever achieved. There is something extraordinary about the situation we find ourselves in. A telescope assembled from components built by thousands of engineers across multiple countries, launched on a rocket that had one chance to succeed, deployed through 344 single-point failure mechanisms over 30 days, cooled to temperatures colder than any natural environment in the outer solar system, pointed at patches of sky smaller than a grain of sand held at arm's length, is returning light that has been travelling since the universe was 290 million years old. And in that light we are reading the record of the universe's first chapter, the one that the Big Bang set in motion, and that our model has been telling one version of for 3 decades. The universe is offering a correction to that version. Not a complete rewrite, a correction, a deepening, a greater precision. By the end of tonight, the JWST timeline problem is not a crisis. It is an invitation. The universe is showing us what it was doing in its first billion years, and telling us that we had some of the details wrong. Getting the details right is what the next generation of observations, of simulations, of theoretical work will accomplish. The Roman Space Telescope, the Square Kilometre Array, ground, based extremely large telescopes now under construction in Chile, the 30-metre telescope on Mauna Kea. Each of these will push the precision of early universe measurements further, tighten the constraints on the standard model, and either confirm or rule out the modifications currently being proposed. We are living through the revision of our best picture of the universe's early history. That is a remarkable thing to be living through. And Webb made it possible. The history of cosmology is a history of the universe repeatedly exceeding the expectations of the people trying to describe it. We thought the Milky Way was the universe, and Hubble showed us otherwise. We thought the universe was static, and Hubble showed us it was expanding. We thought the expansion was decelerating, and Perlmutter and Schmidt and Rees showed us it was accelerating. At each step, the revision made the universe larger, more complex, richer in structure, and more interesting than the model that preceded it. The Webb observations are consistent with this pattern. The universe's first billion years, it turns out, were more productive, more complex, and more structured than our best model thought. The universe is always, in some sense, more than we expected it to be. There is a specific kind of comfort that comes from understanding exactly what you do not know. Before Webb, the first billion years of cosmic history were largely inaccessible to direct observation, and the models that described them were only weakly constrained by data. We did not know what we were missing. Now we have the data. We know, with greater specificity than ever before, exactly which aspects of the standard model's account of the first billion years are in tension with observation. We can measure the discrepancy, quantify it, and begin the work of understanding it. That is a better place to be in than the comfortable ignorance of a model unconstrained by data. Webb's 10-year mission, supported by a budget of approximately $10 billion spent over decades of development, will produce more information about the early universe in its decade of operation than all previous instruments combined. The photons arriving at its mirrors right now, having travelled 13 billion years from galaxies that existed before our solar system, carry answers to questions we've been asking since Hubble first measured cosmic expansion nearly 100 years ago. We are at the beginning of what those answers reveal, and that beginning is already extraordinary. Consider what it means to follow this story from where you are. The Webb observations are not abstract. They are specific photons, absorbed by specific detectors, producing specific numbers in specific files that specific people at specific institutions are analysing right now. The graduate students spending their nights processing NER spec data. The postdoctoral researchers writing code to fit stellar population models. the senior astronomers on telescope time allocation committees deciding which patches of sky to observe next, the theoretical cosmologists running simulation after simulation, trying to produce a model that fits the data. This is not science as a monolith. It is science as a community of people, each doing a specific and necessary piece of work, each contributing to a collective understanding that no individual could assemble alone. The Galaxies Webb has found at redshift 14, the photons of whose light left when the universe was 290 million years old, did not know they would be found. The universe did not arrange itself with our telescopes in mind. The light simply travelled for 13.5 billion years through an expanding universe that was simultaneously building itself into the structure we now inhabit, and it happened to arrive at our mirrors at a moment when we had built instruments capable of detecting it and minds capable of understanding what it meant. That chain of coincidences, the right telescope at the right time in the right place with the right instruments and the right theories to interpret the data, is its own kind of marvel. The Hubble tension and the early galaxy excess are not just cosmological puzzles. They are reminders that the universe's history is more interesting than the simplest version of our model assumed, and that we are the beings on a small rocky planet in one spiral arm of an unremarkable galaxy in an ordinary part of the cosmic web, who have developed the capacity to read that history from the light that crosses the cosmos to reach us. We do not have all the answers. The JWST timeline problem is not resolved. The Hubble tension is not resolved. The nature of dark matter and dark energy are not known. The origin and properties of the first stars have not been directly observed. There is a very great deal that we do not know about the universe's early history. But the difference between not knowing and not being able to find out is the difference between a mystery and a research program. Webb has given us a research program. The questions are getting more specific and more tractable with each year of observations, and the community working on them is larger, more capable and better equipped than at any previous point in the history of cosmology. That is a good place for a species to be in, and it is where we find ourselves. We are grateful you spent tonight with us following it. The link in the description will bring you back if you want to continue the exploration. We have a great deal more to cover. The universe has more early chapters than Webb has yet finished reading, and each one is teaching us something about the world that built us. Sleep well tonight. The universe is still unfolding its early chapters. We have the best telescope ever built to read them. Good night.